Welcome to the course on electron beam machining process. Today we are going to discuss on electron beam machining. In electron beam machining process, there is a bombardment of high velocity stream of electrons on the workpiece surface. So these electrons are bombarded on the workpiece surface with a very high velocity, around 66% velocity of the sunlight. So because of this bombardment of electrons on the workpiece surface, the materials into a small area on the workpiece surface, it melts and vaporizes, and temperature rises to a very high temperature. So material on the workpiece surface melts and vaporizes, and machining is going on. So this process actually it is used for machining thousands of holes on a thin sheet, which is used in aerospace industry, food processing industry, cloth industries, and very high aspect ratio for making of very high aspect ratio holes, thousands of holes on a workpiece surface, irrespective of the material property like metallurgical property, mechanical property of the material. So this material may be electrically conducting or electrically non-conducting, or maybe ceramics, metals, or any kind of metal, any kind of ceramics, it works. So here there is a filament which is heated with a very high temperature. So because of this heating of this filament, so electrons emits from that cathode filament. These filament may be heated from a radiation from another body, from the radiation from another body on a solid block of cathode. On a solid block of filament also it can be generated. So these electrons emits from the cathode filament and it passes through a magnetic lens to concentrate or to reduce the diameter of the electron beam, and it bombards on the workpiece surface. So electron beam machining process, there are two types of methods are there. One is the thermal type, another one is the non-thermal type. So in non-thermal type, these electron beams are used for generating chemical reactions. So for generating chemical reactions, the electron beams are used. So this non-thermal type we are not going to discuss. We are going to discuss only thermal type of electron beam machining process. In thermal type, this cathode is heated to a very high temperature. So this stream of large number of electrons comes as a small diameter beam, electron beam. So the stream of large number of electrons emits from the cathode, from a heated cathode, which comes out as a small diameter beam. So it moves towards the workpiece with a very high velocity, and it bombards. Machining is going on due to the bombardment of these electrons on a very small localized area. So as it is bombarded on a very small localized area, huge amount of temperature is generated on the workpiece surface. So machining is going on due to the melting and vaporization of this material from the workpiece surface from a very localized area. So this kinetic energy of this electron beam is used for the machining to take place, and which converts this kinetic energy of the beam, electron beam, high velocity electron beam, converts into the heat energy. So it can produce holes of different shapes. So any kind of shapes other than circular also can be generated by deflecting the beam at certain angle. So workpiece material can be conducting as well as non-conducting. Any kind of workpiece material can be machined irrespective of their hardness, mechanical and metallurgical properties can be machined by this process. Also another thing is that vacuum is required. So this machining chamber should be vacuum chamber, because these electron beams, when it travels, so if air is there into the chamber, so it will collide on the air molecules. So its strength will be reduced. So that's why this vacuum is generated into the machining chamber. Also this cathode, it is used as a tungsten cathode is used. If air is there, so it will immediately be oxidized. So to reduce or to avoid the oxidation of this tungsten filament cathode, so this vacuum chamber is used. So beam size, this diameter of this beam size should be less than the diameter of the hole to be produced. So ejection of the molten material, how this molten material is ejected, or molten or vaporized material is ejected from the workpiece surface. So at the back side of the workpiece, backing material is used. So after machining on the top surface of the workpiece, so when it reaches to the bottom side of the workpiece, it also vaporizes the backing material. So this backing material also vaporizes, so it comes out as a high pressure. So these backing materials, it comes out as a very high pressure. So while coming out as a high pressure, it also ejects the molten or vaporized material from the workpiece surface. So it expels the molten or vaporized material from the workpiece surface. So at the back side of the workpiece surface, that is a backing material is used. So that's why this backing material is used. So non-circular holes also can be generated by electron beam machining process. Any kind of shape, any kind of shape of the workpiece can be generated by this electron beam machining process. So you can keep a fixed beam, and you can travel the workpiece on a computer numerical CNC table. You can place your workpiece on a CNC table and you can generate any kind of complex shape, or you can move the beam on the workpiece surface using a CNC table. So in both the way, you can generate any kind of non-circular holes on the workpiece surface. So circular big holes can be generated. You can move the beam along the perimeter of the circle, so you can generate the bigger size holes also. So this is the schematic diagram of the electron beam machining process. You can see here, this is the cathode. So you can see here, this is the cathode here. So this cathode filament, it is actually heated up by using a high voltage lead. So there is a high voltage lead is here. So using this high voltage lead, this cathode is actually heated up. So these electron beams, streams of electrons are coming outside from the cathode filament because of the repulsive force from the cathode. So electrons are negatively charged, or here this cathode also they are negative terminal of the power supply. So these electrons are expelled with a very high velocity, and it is coming towards the anode. So it is attracted towards the anode here. So this is anode. So as it is attracted towards the anode, and it is also expelled by the cathode, so it generates a very high velocity. So it is around 66% of the light, velocity of light. So it is passed through a valve where this whatever the stray electrons are there, it is actually filtered. The stray electrons are filtered through this valve, and you can see this one, this what is happening inside this vacuum chamber. So you can see using this optical viewing system. Now this electron beams is passing through the magnetic lens. So this is the magnetic lens. The working principle of this magnetic lens is that, so it actually concentrates all the beam into a certain point. So it reduces the diameter of the electron beam passing towards the workpiece. So it concentrates into a smaller diameter beam. So after that, it passes through a deflection coil, and after passing through this deflection coil, it falls on the workpiece surface into a very small area. So when it falls on the workpiece surface into a very small area, so into that area, into that small area, so because of this bombardment of high velocity electrons, it melts and vaporizes the material. And at the back side of the workpiece, this chemical backing material is used. So when these holes actually extended towards the end of the workpiece, these backing materials also, because of heating, these high velocity gases are generated. So this gas, when it is coming outside with a very high pressure, it expels whatever the molten material is there at the hole. Whatever this molten material, it also expels the molten material. So whatever this recast layer, whatever this molten material, whatever it is redeposited on the workpiece surface, this recast layer can be reduced by this chemical backing material. So this entire chamber, it is actually made vacuum to reduce the possible collision of the electrons with the air molecules. So here you can see there are different elements of electron beam machining system. First one is the electron beam gun, and second one is the power supply, and third one is the vacuum system and the machining chamber. So electron beam gun, so it operates in the pulse mode. So there are some biased electrodes are used. So by controlling this electrode, you can generate the electron beam. So pulse electron beam you can generate. So each electron gun produced focus electron beam on a predetermined location. So there is a superheated cathode is there. Usually it is a tungsten filament which is heated up with a very high temperature, or you can use a solid block of cathode which is heated up by the radiation of a filament. So both things are possible. So because of this heating of this cathode, electron clouds are actually generated surrounding the cathode. So these electron clouds, because of this, these are negative charged, it is expelled because of the repulsive force of the cathode from the cathode, and it is attracted by the anode. It is attracted by the opposite charge anode, and then after that it passes through the magnetic lens. So when it is passes through the magnetic lens, so a converging beam pinpoint at a location can be generated. So this beam is actually pinpointed into a small location when it is passes through a magnetic lens, and also it deflects and make a round beam. So this is the working principle of this magnetic lens. So also these stray electrons are removed by using this magnetic lens, and the diameter of the beam is further reduced. So this switch, it passes through a switch or bias electrode to generate the pulse. So this power supply, it generates a high voltage. So it is around 150 kilovolt. Because of this high voltage, electron beam gun generates the electrons. So this electron beam machining gun is a powerful system. It is operated at 12 kilowatt. Pulse energy as high as 120 joule per pulse can be generated from this electron beam machining gun. So computer control of the process variables can be generated. So all these parameters are controlled from a computer. So high power density is required for melting and vaporization of the material, and it will give the high material removal rate also. And as the huge amount of energy by the collision of these electrons are generated, so material is machined mostly by vaporization of this material. Now this vacuum system and a machining chamber, already I told this machining chamber is vacuum. As the beam actually travels during machining, so it may collide with the air molecules. So that's why to avoid the collision of these electron beams with the with the air molecules, so this machining chamber is made vacuum. So this pressure inside the machining chamber is maintained 10 to the minus 4 to 10 to the minus 6 torr. So because of this vacuum, so there is no oxidation of this tungsten filament. Otherwise, if it is not vacuum, so whatever these oxygen molecules are there inside the air, it will oxidize the tungsten filament, so which is heated up to a very high temperature. So there is no collision of these electrons and the air molecules and no loss of energy of these electrons because of this vacuum chamber. Now what are the different process parameters for this electron beam machining process? So these process parameters are beam current, pulse duration of this pulse. As I told that electron beam machining system, this machining is going on by the pulse mode, not in the continuous mode. So lens current to the lens, magnetic lens, and then beams deflecting signals. So these are the four important parameters for electron beam machining process. So this beam current, it varies from 100 microampere to 1 ampere. So this beam current actually governs what is the energy per pulse. It governs the beam energy per pulse on the workpiece surface. Higher value of this beam current will generate high beam energy per pulse and it will generate the high material removal rate. So by changing this beam current, you can change the beam energy or you can change the material removal rate from the workpiece surface. Now pulse duration, this duration of this pulse varies from 50 microsecond to 10 millisecond. So longer pulse duration will generate wider and deeper holes. So if we put this pulse for a longer duration of time on the workpiece surface, so obviously it will generate a wider shallow hole but a deeper holes because it is kept on the workpiece surface at a certain time for a longer period of time. So it will generate wider and deeper holes, and it affects, this pulse duration also affects the heat affected zone on the workpiece surface. Because of this heating of the surrounding materials, it generates a higher heat affected zone if this pulse duration is increased. So this recast layer in general, the dimension of the recast layer in case of electron beam machining process is 25 micron, around 25 micron. Now lens current, it determines the working distance and focus beam size. So beam diameter, it determines the lens current determines the beam diameter, and also it determines the working distance, and also it determines what is the diameter of the beam. So beam deflecting signals, it affects the hole shape, straight or tapered hole, determined by the position of the focal point below the top surface of the workpiece. This hole shape, whether it will be straight or tapered, it depends on this focal point of the beam, whether it is just top surface of the workpiece or just below the workpiece surface. For non-circular hole, beam movement can be programmed. So other than circular hole, this beam movement can be programmed. Now this material removal rate, it is calculated as eta P by W. So material removal rate in case of electron beam machining process, it is calculated from eta P by W, where material removal rate is rate at which workpiece material is vaporized. So eta is the cutting efficiency, it is around 20% or less than 20% in case of electron beam machining process. P is the power in joule per second and W is the specific energy, joule per centimeter cube, required to vaporize the workpiece material, or W is the energy, specific energy required joule per centimeter cube to vaporize the workpiece material. Now this W can be calculated as CPS Tm minus Ti. Cp is the specific heat, Tm is the melting point temperature of the workpiece material, minus Ti. Ti is the initial temperature of the workpiece, plus CPL. CPL is the specific heat, Tb minus Tm. Tb is the boiling point temperature of the workpiece material, minus Tm is the melting point temperature of the workpiece material, plus HF plus HB. HF is the latent heat of fusion and HB is the latent heat of vaporization. And this S and L, CPS is the specific heat of the solid and CPSL specific heat in liquid. So Cp is assumed to be constant, although it varies with the temperature, but it is assumed to be constant, and suffix SL indicate the solid and liquid states respectively. So from this equation, MRR can be calculated eta into P by W. T is the power and W is the energy required per volume, per unit volume of the workpiece. Now process characteristics, electron beam machining process characteristics. So it can be used for conducting as well as non-conducting material like nickel, copper, aluminum, ceramics, leather, plastics. So any kind of material can be machined by this process. So at the entry side of the beam, it is observed that there is a burst. Because this recast layer or vaporized materials are coming outside, while these vaporized materials are coming outside, so it actually generates a recast layer at the entry site also. So this, because of this recast layer, small amount of bursts are actually visible at the entry site of the workpiece. So this at the entry side of the beam, a small sized bar solidified layer left out. So workpiece properties, physical, mechanical and metallurgical properties do not have significant effect on performance of the electron beam machining process. So workpiece properties does not have any effect on the performance of the electron beam machining process. Hole diameter as low as 0.1 to 1.4 millimeter, a large depth 10 millimeter, and high aspect ratio of 15:1 can be generated from the workpiece surface. So there is no mechanical force because this electron beam machining process, this tool does not touch the workpiece surface, so there is no mechanical force. So any kind of thin and fragile materials can be machined, low strength components can be machined, easily machined by this process. So hence, as there is no workpiece, tool material does not touch the workpiece surface, there is no distortion of the workpiece due to the mechanical forces. Off-axis holes also can be easily generated by deflecting the beams, but there is a thermal residual stress is generated because there is a huge temperature gradient is there, because there is a huge amount of temperature is generated locally at the on the workpiece surface where this beam falls. So there is a huge temperature gradient is there. So because of this temperature gradient,